so I'll be covering today's class. So 30-30, so you have had like 1 week of classes, right? So let me ask you this. What do you think this class is about? So some ideas? Like what is it that this class is planning to talk? I mean, you have looked at the course discussions, right? Descriptions, right? You have?
Maybe we can go over transistors.
Transistors, right?
The physics of why electronic components work.
So yes, so this class is about understanding how the transistors work as well as how the transistors fit into the overall computing paradigms. Transistors is at the bottom of the entire hierarchy, and from transistors you make circuits. From circuits you make systems, you make different put them in different architectures, then they solve different problems, algorithms, and all the way up to softwares, right? So we just want, in this class we want to have an understanding of how the transistors work, how they enable different applications, all the physical aspects of computing. Alright? Okay. Now, how do we do the computations? We know that we represent our data in terms of zeros and ones, right? Bits. And you are all very, very good at digital logic design. You have all seen the gates, the Boolean algebra, all of it, right? So another way of thinking about it is how do we implement the Boolean logic? Like what is it that these devices that do to implement this Boolean logics? Okay. But that being said, when you think about these transistors, what is it really that allows you to do the computation? What is the physical entity that allows you to do the computation? Think about the physical entity. Maybe it's a little bit of vague question, but let me just ask you this. In a transistor, so the idea is that something is on and off. When it's on and when it's off, what is the difference? So when something is on and versus something is off, what is different?
The resistance between terminals?
Exactly. So the resistance between the terminals is different when it's off versus it's on. So basically a switch, when it's on, the resistance is high, though it's off. Resistance is low when it's on, resistance is off when it's, resistance is high when it's off. So the physical entity is actually electrons, right? So what a transistor does is that it controls the flow of electrons in your circuit. So that's the fundamental physics of transistor operation, that you basically control the flow of current, flow of electrons in a transistor. You can, there is another thing called poles, which you will study as well. But the basic idea is that you use electrons, you control the flow of electrons to do the computation in a transistor. Alright. What I'm going to talk about is quantum computing in today's lecture. Alright. So the first thing is that in traditional computing, digital computing, we represent all our data in terms of zeros and ones, or digital bits, digits, 0 and 1. In quantum computing, we do it a little bit different. So we'll just talk about a few things about quantum computing and hope that you will get interested in quantum computing and dig deeper into quantum computing after you have learned the basic computing principles in digital computing as well as whatever you is talking is next. Okay, so how many of you have heard about quantum computing? So there is hardly anyone who has not heard about quantum computing. Why is it so? Why do you hear about quantum computing so much these days? So why do you think quantum computing is interesting?
It's new and faster than traditional computing.
It's new and faster than traditional computing. What does it mean that it's faster than traditional computing? Can you give us an example?
It can dramatically change current cryptography message in a very large way.
So current cryptography methods in a fundamentally, it can have a fundamental impact on cryptography. That's what you're saying, right? All right. So yeah, so there are certain applications where quantum computing can have a revolutionary impact, and so that's what I'm going to talk a little bit about, and then I'll also try to talk about a little bit about what quantum computing is, what does it mean by the quantum part in quantum computing. All right. So this is the first thing that everyone shows in a quantum computing lecture. First thing is that if you Google quantum computing, you'll see that quantum computing will change the world, and another search is quantum computing will never work. Okay, so with that being said, this is another famous photo now. Can you guess what is happening in this image? And why are we talking about President Trump in quantum computing?
Well, it says National Quantum Initiative to sign.
Yeah, so President signed into a law $5 billion investment in $50 billion investment. 50 or 5, I don't remember. Probably 50. $50 billion investment in next 5 years in quantum computing, right? So that's kind of a big deal. That means that a lot of innovations will happen in next 5 years in quantum computing. And the reason is that right now there is a very important need for the technologies that quantum computing can enable, as well as it's a global competition because all the other places, including China and Europe, has been spending a lot of money on this research. So that's why in the United States there has been a significant thing, so that there is significant amount of new innovations that happens in quantum computing going forward. So this is called a hype chart. It's called a Gartner chart. Anyone familiar with this one? Okay. So this means that if any technology that comes in, it goes through a cycle like this. First it's here, then when it goes here, everyone talks about it, and that fails at some point, then comes back again. Okay. So for example, you can think about autonomous vehicles. Maybe 10 years back, everyone was talking about it, then it reached some height, then you had a number of crashes, all the interest went down, and then it steadily made a progress. So it's kind of a, says that. And quantum computing, in this chart, 3 or 4 years back, it was right here. So that's that. So it's like says that quantum computing is interesting going forward. All right. So let me tell you as to why quantum computing is interesting from an application, like certain applications. So do you know RSA cryptography? Like for example, how do you transfer, like, know about secure lines, right? Or like I mean, in the movies you see that someone is calling someone on a secure line, or the bank transaction information are sent over the internet, right? It goes through a certain, it happens through a certain cryptography scheme called RSA cryptography. And what it essentially does, it, like, say you are given a 1028-bit number, 1028-bit number, and say this is it's a product of 2 prime numbers. And the thing is that unless you, by looking at that big of a number, 10 power, so this number is how big? So 10 power bit. So what is actually, like, the number itself is like actually this big. So it's like a very large number. And you cannot actually factorize it classically unless you know the key, meaning that if you don't know one of the prime numbers, you cannot guess the other prime number in a reasonable amount of time. Okay, so that's why our cryptography schemes in current world works, meaning that if you have this kind of number, you cannot factorize it into two prime numbers, and as a result, all our cryptography schemes are working fine. Okay. What quantum computing, the reason quantum computing became very interesting in early 1994 is because someone named Peter Shor showed that if we use quantum mechanics to do computation, you can actually break this, you can factorize these numbers very quickly. That's where all the interest in quantum computing started in 1994. So let me show you some numbers, some ideas. For example, if you want to factorize a 2048-bit number into two integer primes, you will need a supercomputer of the size of Germany that runs for 100 years and consumes all the energy of the earth that we consume. That much of computation power will be needed to factorize a 2048-bit number. All right. So you understand that this is you practically cannot factorize a 2048-bit number classically. Does it make sense? Is it clear? Now the thing is, if you have a quantum computer, provided it can do a certain physical qualities, this thing can factorize a 2048-bit number in 26 hours. Alright? Does it make sense? Do you understand that why quantum computing suddenly becomes very important? So let's get back to 1994. Peter Shor says that this algorithm, using quantum computing, you can do all these amazing things. Alright? Suddenly everyone gets interested in quantum computers, including banks, security agencies, everyone. Why? So why do you think that as soon as Peter Shor shows that algorithm that you can do integer factorization very easily, everyone gets super excited and also scared? Why do you think?
Because it'll break a lot of our current cryptography.
It will break a lot of our current cryptography. Right. So think about at that moment, if anyone has a quantum computer, then he or she or the agency can break into all the secure communication that is happening all over the world. So that's why at that point a race started, first to make quantum computing and also to have new protocols of security that cannot be broken with quantum computing. So that's a whole big deal at that point. So that's where the entire thing started. So now if we go back to quantum computing again, the idea of quantum computing was first proposed around 1980s. Actually even before that you can use quantum systems to simulate a classical, something that a classical computer cannot simulate. Then 1994, the Shor's algorithm came in and kick-started all the current efforts on quantum computing and so on and so forth. There are many things that happened over the years. Okay. So now when we say that, what is quantum computing? We are saying that we are using quantum systems. But what is quantum system? For that, let's get to this idea about this. Okay. Let me show. Okay, so just to give a sense of quantum algorithms, what it is, let me give you this problem. Say you are given a function f of x. say x, the value of x can be 0, 1, all the way up to 2 power n minus 1. Right? Say if n equals 3, you have 8 numbers. Okay. And f can be either of two types. It can be either a balanced function or it can be a constant function. Or f of x can be 0 for half of x values and 1 for other x values. So say you have a function fx which can be a constant for all the values of x, or f of x can be a balanced function where for half of the values of x it's 0 and for half of other half it's 1. Right? So let's call it the constant function and this is the balanced function. Okay. So say you have the number, so say x can be 0, 1 all the way up to 7. So you have 8. X can have one of these 8 values. How many trials would you need to find out whether f is a constant function or f is a balanced function? So how many times you need to do an experiment to find out whether fx is a constant function or a balanced function?
A little more than half, or one more than half?
Little more than half. So basically, so say you have 0 through 7, right? You do 0, 1, 2, 3. So you have input 4 number. In all cases, say you have gotten 0. Alright? Now then you do another one more number, and if it comes out to be 0, then you know that it's a constant function. On the other hand, if it's the fifth one that you try comes out to be 1, you will know that it's a balanced function. So to know whether this function is a balanced function or a constant function, you need to do at least 2 power n plus 1 number of trials. In this particular case, you will have to do 4 plus 1 equals to 5 times. So you have to do the experiment 5 times to know whether f is a balanced function or a constant function. Right? What is interesting is that if you can use some quantum properties in your hardware, it's quite amazing that using an algorithm called Doi-Jobs algorithm, you can do this, you can determine whether fx is a constant function or a balanced function by just doing one trial. Right? So that's amazing. Think about it, if n is as big as 10 power 24, then see how many numbers that you need. Say for example, n is 20 or 10, then you will need at least 500 or something close to 600 number of trials here. On the other hand, with this Doi-Jobs algorithm, you can do the entire thing in one shot. So that's kind of the power of quantum computing. For certain applications, certain kind of tasks, you can exponentially reduce the number of tasks that you need to achieve any computation. So that's the main thing here. Alright. Now the thing is, why is quantum, like, how do you get all these properties from, how do you, what is it that you leverage to get that kind of a speed up in computing, in quantum computing? And the idea is that you use quantum mechanical phenomena of your computing entity. In classical electronics, as we are saying that an electron is flowing, and what we are doing is just allowing it to flow or not allowing it to flow. That's how our digital electronics in today's digital electronics works. In quantum computing, we use two other quantum mechanical phenomena of our computing entity, it can be an electron. And the first thing is that of a superposition, and the second thing is entanglement. All right. So what does superposition mean? How many of you had a quantum mechanics class sometime back? Okay, a few of them. How many of you have heard about Schrodinger's cat? You have seen at least a number of memes, right, of Schrodinger's cat. So the idea is this. In classical world, we can say that something exists or doesn't exist. All right. Say, Schrodinger's cat means that if you have a cat in a box, you don't know whether the cat is alive or dead after a certain time. Okay. It can be both alive and dead at the same time. So that was the basic idea of all the memes. Not exactly the quantum computing idea or quantum mechanics idea, but that's the thing. In quantum mechanics, everything is related to everything is described by something called a wave function and probability. Okay. So for example, you have a billiard ball in your hand or a tennis ball in your hand, and you throw it and you know exactly how it goes and comes back, right? Think about it in quantum mechanics. You have shrunk everything to quantum mechanics and you have, say, an electron. And the way, as soon as you go to this microscopic region, the electrons are no longer described classically. What does it mean? It means that it can only be described by a probability. For example, say you have a box. Say you have a box, you have an electron. You put an electron there. And you allow the system to evolve of some time. And after some time, you can classically the electron is supposed to be there. But quantum mechanically, there is a probability that it is inside the box or it might not be inside the box. So basically, something can exist as a probability of being there in that state or not being in there in that state. One example of quantum mechanical phenomena is called tunneling. How many of you know about, heard about tunneling? Okay, so just to give you an idea what quantum tunneling is, say I am a big particle here and there is a wall here, right? Since I am not very strong, I don't have muscles, I cannot probably get past this wall, right? I cannot break it and I cannot also jump over it. Right? In quantum mechanics, something unusual happens. And what unusual happens is that even if there is a wall here, the electron has a certain probability to pass through this wall. And that is what is called quantum tunneling. Okay. So this is one example of how things are different in quantum regime. And quantum regime means extremely small at this point. Extremely small. So what we were talking about is that in quantum mechanics, there is this concept of superposition where a bit can either be 0 or 1 at the same time. Okay. So in logic gates, you have studied zeros and ones, right? Something in the truth table, something can be 0, something can be 1, right? Always entries in the truth table, right? In quantum computing, what happens is that a bit can be both 0 and 1 at the same time. Does it make any sense? It should not make any sense, but that's what the reality is. Okay. So again, a bit, so we can represent a bit like this. And say if it's up, it's 0, and if it's down, it's 1. In classically, a bit can be either 0 or 1. In quantum mechanics and quantum computing, what happens is that a bit can be in between them. Alright?
you detect a bit in between.
Exactly. So the thing is, now if you measure it, say for example, if you measure it, in this particular case, you may measure it to be 70% of time up and 30% of the time down. So if you measure it 1,000,000 times or 100 times, 70 times you will get it up and 30 times you will get it down. So that's the thing about qubits. Alright. So that's the thing. Now, that's what is called superposition. And at a given time, a bit can be in both states. That's it. Second thing is entanglement. And what entanglement means that what you will measure out of this 2 bits will depend on what you have measured in the other one. Okay. Say you have 2 bits that looks like this, and when we write it like this, 0, 1 and 1, 0,